Hello everyone and welcome back to Causality with Boris, all broadcast from Sobolev Spaces. In this video I talk about computing treatment effects, intervention probabilities, backdoor adjustment formulas, and minimal adjustment sets are the three main things in this lesson. Make sure you watch chapter 3. I'll explain the mechanics of the adjustment formulas using graphs. I prepared an extra material for this video. To receive it, click on the link in the description and the PDF will be sent to your inbox. Causal reasoning relies on the premise that there is a mechanism that links treatment and outcome. Mechanism reveals itself through data, and then we summarize data using the joint distribution for all variables involved. How do we represent the mechanism then? Well, by factorization of the joint probability through a product of conditional probabilities defined for each variable given its parents. Computing treatment effects is based on these conditional probabilities. We use them to predict responses to studied treatment, or in broader terms, to intervention. The conditional probabilities can be estimated before the intervention. Then we derive the post-intervention distribution of variables from these pre-intervention probabilities. And for this we use assumptions encoded in the causal diagrams. We then compute the treatment effect by contrasting intervention probability of outcomes under different treatments. What does it mean in practical terms? We estimate conditional probabilities of outcome for each treatment in strata set by variables that block all open backdoor paths. We select stratification variables from all non-descendants of treatment that disseparated from outcome. Let's say it on paper. The top square shows conditional outcome probability in two strata determined by variable z. Within each stratum, the outcome probabilities correspond to treatment groups. Think about the distribution of units between treatment groups and assume they are influenced by pre-treatment conditions. Then outcomes follow pre-intervention probabilities. They naturally occur due to underlying stochastic processes, the same processes that generate data we observe without any intervention. Post-intervention probability of outcome, or intervention probability for short, is computed then this way. We take a joint distribution, then we set the treatment variable to the value that represents the intervention, and then we replace the treatment probability with the value of 1. Then all univariate conditional probabilities are computed for the set value of the treatment variable. Look at the bottom portion of this graph. It shows the marginal outcome probability for two treatments. We compute them using the orange rectangles. Consider two treatments and categorical variable z. The probability of the potential outcome, if all were treated, is simply the average of conditional outcome probabilities. Averaging is done over the distribution of variable z that satisfy the backdoor criterion. Note that conditional probabilities are observed in the treatment group, and we average over the distribution of z in the entire study population. Then the probability of the potential outcome, if all were untreated, it's the average of conditional outcome probabilities from the control group. Again, we average over the distribution of z in the study population. This equation has several names. In early days we call it stratification estimator, and most recently the adjustment formula. It works for continuous outcome too. Intervention probabilities become the intervention distribution function. We simply replace conditional risks with conditional means and marginal risks with marginal means. Back to the blue board. The mean potential outcome is simply the average of conditional means over the distribution of variable z that satisfy the backdoor criterion. Again, conditional means come from the treatment group and averaged over the distribution of z in the study population. For the mean outcome, if all were treated. If all were untreated, conditional means come from the control group. Still, the averaging is done over the entire study population. And the total treatment effect is the difference between the mean potential outcome for all treated and all untreated. I'll use mosaic plots again, this time to show how the adjustment formula works. Variable x is treatment, variable y is outcome, and z is a stratification variable. All three are binary, they either 0 or 1. Let's start with the square unit in the middle. It shows 4 vertical bars, one for each treatment group across strata defined by z. For instance, the bar on the left corresponds to x and z with value 1. The study population is equally divided between two treatments in this graph. However, they are not equally divided between strata. Z0 has more units with control group than Z1. Then vertical bars are split into rectangles. Their areas are joint probabilities for all three variables. The heights of these orange rectangles are conditional probabilities that y is equal to 1 for given x and z. We check for treatment outcome association by comparing their heights. The outcome probability in control group is higher than in treatment group in both strata, but the difference varies across strata. It's 1 in 12 for Z1 and 1 in 6 for Z0, twice as frequent. Now let's turn to plots on the sides. They show the mechanics of averaging. It's done in two parts. First, we stratify on conditioning variables, then divide strata in treatment groups, and then estimate the risk of outcome by treatment in each stratum. That's part 1. Here's the part 2. We project the outcome probability that the treated would have experienced had they been untreated. For this, we take the outcome probability in the control group and apply it to observations in the treatment group. And we do this in each stratum. And then we average the projected probabilities over the strata. That was the mosaic plot on the left. Now let's project the outcome probability that untreated would have experienced had they been treated. We take the outcome probability in the treatment group and apply it to the control group, again in each stratum. And then we average the projected probabilities over the strata. The plots at the bottom show the results of this averaging. On the left is the expected risk of outcome in the population of all treated units. It's 13 and 32. The other is in the population of all untreated units. It's 13 and 24. So the total treatment effect is the difference between the two, and it's about 1 in 7. You saw these formulas before. What changed? Why am I so excited? Isn't we just attach the backdoor criterion label to these known formulas? The choice of stratification variables is the answer. Before, and I mean as in 1976 before, so that before we argued that within individual stratum, the treatment outcome association is free of influence from stratification variables. Indeed, stratification variables stay constant within each stratum. But now we find these variables using the backdoor criterion, and it guarantees that the association is not due to other factors either. Stratification on variables that meet the backdoor criterions blocks all other influences. How is it not exciting? What if Z includes many variables? Then we may not have data to use the adjustment formula. But before running in demanding regression adjustment, consider this. The adjustment criteria usually give more variables than needed for conditioning. Look at this diagram. We can find 7 distinct adjustment sets satisfying the backdoor criterion relative to the effect of t on y. 3 pairs, x1 and x4, x2 and x4, and x4 and x5. 3 triplets, x1, x2 and x4, then x1, x4 and x5, and the last triplet x2, x4, and x5. Then a set with 4 elements x1, x2, x4, and x5. Looks like we have more sets than we would be enough for conditioning. For example, x1, x2, and x4 intersects with x1 and x4, and with x2 and x4. Is there a way to settle on a minimally necessary set? What's a minimal set? Well, it does not contain any other set sufficient for conditioning. Insufficient means only needed variables. In this example, triplet x1, x2, x4 is not minimal. Consider a sufficient set with the smallest number of covariates, and then I call it minimally necessary adjustment set. Complex causal diagrams may contain many backdoor paths. So identifying sufficient set may be time-consuming. There are several software applications to help us. My favorite is Dagity. Watch my tutorial on Dagity. It will advance your skills in finding non-causal paths, backdoor paths, and conditioning variables. In this video, you learned about computing treatment effects. Here is the main message. Stratify on variables that meet the backdoor criterion. The stratification guarantees that within each stratum, the treatment outcome association is free of influence from stratification variables. And the backdoor criterion guarantees it's not due to other factors either. Don't miss chapter 3. It walks you through the graphical explanation of adjustment formulas. And remember this idea. We project the outcome probability the treated would have experienced had they been untreated. And then we project the outcome probability the untreated would have experienced had they been treated. That's all there is to it. Keep on watching.